Okay, so today we're going on a quest, but not for gold or anything like that. We're on a quest for something way more precise, the perfect cut. We're going to be looking at these incredible machines that can slice right through solid steel. But you'll see, the real magic isn't just the machine itself. It's about finding the absolute perfectly dialed-in settings. And we're going to dive into some really cool research that did exactly that. What you're looking at right here is a CNC plasma cutter. Seriously, this thing is an engineering marvel. It uses a jet of ionized gas, that's plasma, that's hotter than the surface of the sun to just blast through metal. But with all that power comes a huge challenge. You see, the tiniest little change in speed or pressure, or even the nozzle, can be the difference between a perfect part and a worthless piece of scrap metal. And that right there is the big question this whole research project set out to answer. We know, finding the best possible setup isn't just for bragging rights. For manufacturers, getting this right means saving a ton of time, a ton of money, and a ton of materials, all while making better parts. So how in the world did they solve this puzzle?
Well, first, let's do a super quick refresher on the technology at the heart of all this. What even is plasma?
You probably remember solid, liquid, and gas from science class, right? Well, what happens if you just keep heating up a gas? You get plasma. The energy gets so intense that it literally rips electrons away from their atoms. And that creates this electrically charged, super hot substance. That's what gives a plasma cutter its unbelievable power. And to put that kind of power into perspective for you, an acetylene and oxygen flame, which is one of the hottest flames we use in industry, burns at around 6,300 degrees Fahrenheit. That is more than hot enough to melt and vaporize metal almost instantly, which is exactly what's happening inside that cutting torch. Okay, so with that incredible power in mind, let's get to the experiment. The first phase was all about finding the best operating parameters, and you can really think of it as a battle of the experts. So what's so interesting here is how the researchers tackled this. They realized that pretty much everyone had a different opinion on the right way to run the machine. The company actually using it had their own preferred settings, the machine manufacturer had their recommendations, the company that made the nozzle had a third set of rules, and then the company's own internal R&D team had their own theory. So you know what they did? They put them all to the test head-to-head. Each of these 4 recipes was judged on 3 really critical things. First, how accurate was the cut. Second, how smooth was the surface it left behind. And third, how much material was just vaporized and wasted in the process. It was a true competition to find the one superior method. So after they ran all the tests, which set of parameters actually won? Let's break down the results.
First up, accuracy. The whole goal was to cut a part that was exactly 100 millimeters. Well, the R&D department settings, they produced a cut with an average dimension of 100.066 millimeters. That was, by far, the most accurate result out of all 4 contenders.
Next up, the surface finish. This is measured in something called roughness average, or RA. A really simple way to think about it is like the grit on sandpaper. The lower the number, the smoother and higher quality the cut is. And guess what? The R&D parameters won again, delivering the best performance with a roughness of just 0.025.
And finally, we have material waste. This just measures how much metal gets vaporized and blown away during the cut. Obviously, less waste means a cleaner, more efficient process. And, you guessed it, the R&D settings came out on top again, removing only 0.020 grams of material. So after that first battle, we had a clear winner. The R&D department's recipe was just plain better in every single category. This was huge because it gave the researchers a solid, optimized foundation to build on for the next, and even more important, phase of the experiment. So with the best settings now totally locked in, the focus shifted to the single most important component for aiming that jet of plasma, the nozzle itself.
The nozzle is basically the business end of this whole operation. It's what takes that chaotic, superheated plasma and focuses it down into a precise cutting stream. Its size, its shape, and how much it wears down during use, all of that has a massive impact on the final cut. You could have the most perfect settings in the world, but if you use the wrong nozzle, it'll ruin everything. So, for the final showdown, the researchers took their new champion settings and used them to test 4 different sized nozzles. They tested everything from a tiny 1/32 of an inch all the way up to 5/64 of an inch to see which one would deliver the absolute best results. All right, this is it, the final round, the ultimate test to find the one single best combination for that perfect cut. Let's look at the data. Just look at that row for the 3/64-inch nozzle. For accuracy, it hit 100.034 millimeters. That is incredibly close to perfect.
For roughness, it scored a mind-blowingly low 0.008. I mean, that's an unbelievably smooth finish. It also wasted the least amount of material. But here's the kicker. Look at the wear. The nozzle's critical pin diameter started at 0.90 millimeters and ended at 0.90 millimeters. It showed basically zero wear, while all the others started to degrade. It was a total clean sweep.
And the researchers' own conclusion really says it all. After this methodical two-stage experiment, they found that the 364-inch nozzle, paired with the R&D department's settings, was without a doubt the best combination. No arguments, no ambiguity, just clear, data-driven results. So what's the big takeaway from this whole quest? Well, it shows us that getting peak performance in manufacturing, it's not about guesswork or just hoping the factory settings are good enough. It's achieved through a rigorous, scientific process of testing, measuring, and optimizing every single variable you can think of.
This entire massive effort was focused on perfecting one small but really critical industrial process. And it kind of leaves you wondering, right? What other systems or products or processes in our daily lives could be dramatically improved if we just took the time to look this closely and test this methodically? What other perfect cuts are just out there waiting to be discovered?